There are two talks. Sorry, yeah. There are two talks, and the first one is by Abhishek Dhar, and he's going to talk about page curve entanglement.
Okay, thanks, Shotto. And yeah, first I would like to thank Tridib and Gautam and Jacopo for inviting me to give this talk in this very nice meeting. Yeah, mic is not very. Okay, so yeah, okay, sorry, the title is a bit different than what I had given. It's about hydrodynamics, trying to hydrodynamics of entanglement, but it's basically trying to looking at a freely expanding gas and looking at the entanglement dynamics. Okay, so this is work done with Madhumita Saha, who's a postdoc at ICTS, Tamogna and Tharva, who are students at ICTS, Manas, who's a colleague here. So I think most of these people should be here or are here or should be here, and David Hughes. Okay, so so some of this work is published here, and some of it is ongoing, like very recent work, which I'll talk about. Okay, so I'll just give some very quick motivation. I mean, so originally the motivation was to understand, like I have a toy model to understand the black hole information loss paradox. So basically, let me quickly, very briefly state the paradox. So basically, I mean, a black hole is formed, let's say it's in principle, it's a pure state, and it has some wave function which has detailed information of what the star is made of, and where the atoms are located and so on. So it's a, basically black hole is like you have a lot of matter which collapses and forms some pure state. Okay, so then what we know is that what Hawking argued is that a black hole actually radiates and eventually vanishes. So the final state is just thermal radiation, which is a mixed state that depends on very few parameters. Okay, so so basically the information loss paradox is that all the information in the initial state is lost, and this is the paradox. So one way to sort of quantify is through this entropy. And what Hawking showed is that he did a semi-classical calculation, and he showed that the radiation entropy of the radiation that's emitted by the black hole keeps increasing till the time the black hole vanishes. Okay, so you have a lot of entropy generated, even though your initial entropy was it was a pure state, so there was no entropy. So, so this was the kind of paradox. So there was a, so there's another very famous argument related to this black hole paradox, which was argument given by Page, who argued that if you look at the entanglement entropy of the black hole with the radiation, then initially, let's say there's no radiation, it's just the black hole, so there's no entanglement. And eventually the black hole completely evaporates and you just have radiation. So the entanglement entropy has to increase. I mean, as the black hole radiates, there's entanglement between the black hole and the radiation. But eventually the entanglement has to go to zero. Okay. So you will get what's known as a Page curve. If you plot the entanglement as a function of time, then it has to go up and eventually it has to go down. Okay. So he, I mean, I mean, he basically argued that if you assume that I mean, the black hole and radiation form maximally entangled state, which is the case where if it's a random pure state, then basically you can show that the entanglement has this sort of linear Page curve. Okay, so I won't go into the details. And so this is a long time paradox, and recently it seems this paradox is resolved, though there are like a lot of debate. There's one interesting article that I really like by Christian Mies, where he takes the point of view of a statistical physicist, and one can ask, is there really a paradox? So this anyway, so anyway, so the in a nutshell, this is the kind of paradox. So you look at the entropy as a function of time, between the, so this is the entropy of a radiating black hole. So what Page showed is that the entanglement entropy has to follow this curve. Okay, it has to go up. Initially, it's completely unentangled, and eventually the black hole completely radiates. So it has to be, there's no entanglement. So it has to follow this curve. Okay. What Hawking showed is that the entropy of the black hole seems to keep increasing, and so resolving this is the main paradox. So what we wanted to do is basically, so the outline of the present work is, can you just have a very toy model which basically reproduces the basic features of the Page curve. And I want to say that we want to sort of look at the dynamics. So the simplest thing one can think is like my black hole is like particles in a box. And then I just open the box and it escapes. And I just ask for the entanglement between the particles in the box and the particles that have escaped. So this two halves, right? Okay, so so it's basically free expansion of an ideal gas into the vacuum, and so in this simple model we can completely understand the shape of the Page curve and so on. So there was, around the time we started this work, there's also related work by these people, and actually in the more gravity community also there was a related work. So this is a very interesting work where basically you consider again a one-dimensional line, and where you have you just have a moving mirror which is moving, let's say, to the left with an increasing speed. Okay, so it's accelerating, which means it will radiate radiate photons. And then basically what was computed was the entanglement between the part of the system towards the between the mirror and the origin and the remaining part. Okay, so here they again computed a Page curve. So the calculation basically involves a free bosonic field. So using conformal field theory methods, this was computed. Okay. So in some sense, this is kind of, our model is kind of close to this, but it doesn't have the gravity aspect. Okay, so so what I will show is that we have results from exact microscopic numerical calculations. Because it's free fermions, you can do very accurate microscopics. And we can understand this from a semi-classical generalized hydrodynamics, and there's very good agreement between the two. Okay, so that's the interesting, most interesting result. Okay, so of course there's no gravity, no interactions. So, but our model seems to capture some important aspects. And in particular, we point out that there are different forms of entropies are involved. There's Boltzmann entropy, there's entanglement entropy, there's von Neumann entropy, and so on. So one needs to be careful about what exactly one is talking about. So for example, the Boltzmann entropy of the radiation, we show that it actually keeps increasing, while the entanglement entropy does follow the Page curve. So, I mean, this is, in some sense, this is what we would say that Hawking's calculation shows. Okay, so apart from this kind of motivation, of course, independently, entanglement is a sort of important measure of quantumness, and understanding entanglement even in non-interacting many-body systems is interesting, and it's already quite non-trivial. Okay, so this is just motivation. So now let me define them. Okay, so I should just say some earlier related work. So first of all, there's a lot of work on what I would say static Page curves, which is basically like you look at a system, let's say, for example, an eigenstate, and then you compute entanglement between two parts, and see how entanglement grows with subsystem size. Okay, for dynamics, there's a lot of work on like domain wall initial conditions and homogeneous Cohen's initial conditions. This is the famous work of Calabrese and Cardi, where some interesting, like some of the first results were obtained, and then there's a lot of other interesting work. So some interesting findings are for this particular domain wall initial condition. So it's just like let's say on an infinite line, like half of it is fully filled. So it's a lattice where half the sides are completely filled, half the sides are completely empty. and then you ask for the entanglement between the two halves. Right. So in this case, this paper showed is that in general, for low entropy initial states, the entanglement grows as logarithmically in time. While if you look at high entropy initial states, then the entropy growth is linear in time. Okay. The other interesting thing is that even if you start with the same initial condition, if you have a defect site at the junction between the two domains, then again this log t changes to a linear growth. So this is something we'll actually also try to understand. Okay, so this linear entanglement growth dynamics has been understood from hydrodynamics, and this log t growth is more difficult, and it requires fluctuating quantum hydrodynamics. So there's work by many people, but I just write this paper. So there's also some work on interacting systems, which I won't talk about. Okay, so let's define the model. So this is the model. So we just have a tight binding model. So this lattices. So this is from sites, let's say -n+1 to 0. I'll call the system, and this is like the bath. Okay, and so there's this hopping G between every sites, and at this site we put a defect by putting there's some on-site potentials at this site 0 and 1, and then there's some different hopping at this on this bond. So this is the system connected to the reservoir with some different hopping element and some on-site potentials here. Okay, so this is the Hamiltonian system, reservoir, and then coupling. Okay, so this is what I would think of black hole, and this is the radiation, the bath. Okay, so at the system path interface sites, okay, so this I already mentioned. And what we'll see is that I already mentioned that if you didn't have this defect, then the entanglement will grow logarithmically with time. If you put this defect, then it grows linearly with time. So the entanglement helps in generating entanglement between the two paths. Okay, so we'll always start with initial states which are Gaussian. So this particular field state is a Gaussian state. And in the, okay, so basically the initial state is some Slater determinant. Okay, so one can consider various kinds of defects. And in particular, I want to mention this something called a conformal defect, where you put this these two on-site potentials and this coupling in such a way that if you look at now transmission of waves from this side to this side, the transmission coefficient Tk is independent of the wave vector. Okay, so this is, you can just choose a particular way this parameters. Okay, so I'll mostly present for these results for this conformal defect. But the, so most of what I'll talk will also be true for other kinds of defect, where you might just have a bond defect or might just have on-site defect. Yeah. So the defect, so when electron goes, if without defect, it will just go through, right? If there's a defect, then it's kind of broken up. There's a transmitted and reflected, and this creates more entanglement. So it just generates more entanglement, right? Yeah. Okay, yeah, this is exactly the point. Okay, so with the defect, it grows, and the reason we introduce a defect is that you can understand it within generalized hydrodynamics. You don't need fluctuating hydrodynamics. Okay, any questions? I hope the model is clear. Sorry? Sorry, yeah. So this was transmission coefficient versus wave vector. The green line is conformal defect. The others are the other kinds of defects. Okay, so now given this is a non-interacting system and our initial states are Gaussian states, yeah.
Entanglement entropy?
Same as?
This flat line.
Yeah.
it is independent of the, oh, this is K.
This
not
is just the
time.
transmission coefficient, right?
Okay,
It's
okay,
not,
sorry.
not yet the,
Okay, sorry, I thought it was time axis.
yeah,
Okay.
sorry. So this is entanglement into, sorry, just the transmission of plane waves as a function of wave vector. So the conformal defect is special in the sense that it's independent of K. Yeah.
The defect, you said that if we start from a low entropy state, then it increases with log T, with high entropy states increases linearly with T. So is there any physical reason for that?
Okay, simple way to understand is like if you take a high entropy state, like high entropy state, even if you compute entanglement between, let's say, subparts, okay, this satisfies what is called a volume law. So the entanglement increases as system size. Okay. Now, when particles escape, you can imagine that they're carrying, some entanglement per particle, and it will be proportional since the escape is linear in time. So the entanglement will be kind of also proportional to time. Right, yeah, if you just compute within this system, if you take a subsystem and ask how it grows with system size, like subsystem size. So if it's a low entropy state, it grows logarithmically with L, while for high entropy state, it goes as linearly with L.
But then it seems like as entropy is increasing, with increasing entropy, the increase also increases. But is the coefficient different, or these are just the rates?
Yeah, I think the coefficient is also more. I think it's the same.
It's the same. Okay.
Right. Yeah. Right. Okay. Okay. So. Okay, so for this kind of system, the 2-point correlation matrix has all information that we are interested in. So okay, so for this lattice model, the spectrum is this epsilon k is minus cos k, and for Gaussian states, we compute this. So psi t is any slated determinant pure state, and then this is the correlation matrix, and this has all information. Okay, so its time evolution is just given by this. It's a simple free particle evolution, and then, for example, if you want the density profile in the system, it's Ci dagger Ci, so it's just the diagonal elements of the correlation matrix. If you want total number of particles in the box, that's a sum over this. The particle current is can be obtained at the junction. We can ask what is the particle current, and we can compute number fluctuations and so on. For the entropy, if you want the entanglement entropy, so for, again, this kind of Gaussian states, so first one has to find the reduced density matrix. And if it's a Gaussian state, the reduced density matrix will have this structure. And then from this, okay, so one can show that this matrix is basically given in terms of the correlation matrix. Okay, so we have to look at the correlation matrix for sites ij in the system. So A is the system. And then if I look at the spectrum of this, that basically, from the spectrum of this correlation matrix, I can compute the entanglement entropy. So rho A is the reduced density matrix, either in system or in the reservoir. And this is the entanglement entropy, and it can be written just in terms of the eigenvalues of the correlation matrix. So this correlation matrix is, it's basically this matrix, but defined on sites within the system. Okay, so this is the, what we can, just from microscopic simulations, we can compute this. Okay, so now I'll talk about the hydrodynamic description of the gas. So basically, one can think of the gas as a system as a gas of quasi-particles, which are localized both in position and momentum. And we can talk of some phase space density NTXK. Okay, so then in the semi-classical description, basically these quasi-particles have some group velocity, which is just from the single particle spectrum, we take a derivative, and that gives the group velocity. And these quasi-particles do not interact. So the evolution is basically, this is the Euler equation. And this is basically like simple kinetic theory with no collision terms. Okay. And this is also the simplest example of GHD, where this velocity is kind of trivial. Okay, so more formally, one can actually derive this as a coarse-grained Wigner function. And let me quickly talk about this. Okay, so given the many particle wave function, one can construct this single particle density matrix, and then one can construct the Wigner function. So this is this is still here; it's exact. And then if one does some small coarse graining of this Wigner function over a length scale h bar, then one essentially gets this the phase space density. And this phase space density satisfies this Boltzmann equation. Okay, so a nice derivation is given in this review. Okay, so now, okay, so I talked about microscopically, you can find the eigenvalues of the correlation matrix, and from that one can compute the entanglement entropy. Now, from hydrodynamics, how does one compute entanglement entropy? So first I'll just discuss another definition of sort of a definition of entropy that can be computed from this phase space density. Okay, so so once we have this phase space density, okay, so for example, just the density profile is of course just obtained by this. Now one can compute something which I'll call a hydroentropy at a point x by integrating over all momenta this function. Okay, so this is n log n plus 1 minus n log 1 minus n. So now the way to think about this is just locally. I mean, there's some Fermi distribution, and I can ask what's the Boltzmann distribution locally, right? So then n log n plus 1 minus n log 1 minus n integrated over dk is actually the Boltzmann entropy at a local cell. Okay, so so this was actually defined by Yang in '69, and it has been studied a lot in the relation to entanglement entropy in earlier work. Okay, so now using this, we can compute the entropy of the system and of the reservoir. Okay, so system is from minus n to 0. So we just integrate this entropy in the system part and the reservoir part. Okay, any questions? I hope this. This row is the local density of the at any point, yeah, of the using the full wave function. Single particle density, yeah.
Yeah, instead of coarse graining, you said that you can get the Euler equation from coarse graining, the single particle. So another way is to think of the many particle Wigner distribution.
But I constructed what I wrote is the many particle Wigner function. See, like from the many particle wave function, I computed the single particle density matrix, and then I constructed the Wigner function. So, but in some sense, it has the information about the many particle, yeah. But it's because it's non-interacting. It's essentially like a.
But if you do the sum, the many particle sum, then actually this Euler equation does follow in the h bar going to 0.
Yeah. It's you can, but I mean, yeah, you can take just the h bar going to 0 limit and also obtain this.
Yeah.
But yeah, that's one way to think. But you can also like think of it as some coarse graining in. I think it's the equivalent.
I see.
See, I mean, otherwise, like the Wigner function, for example, in general, can be negative and so on, right? But if you do this coarse graining, you're guaranteed that it's a positive function.
Or if you sum over, all the occupied states in a particular Slater determinant state. I'm saying
if
that
you sum over all, then of course it's.
Then the negativity goes away.
Yeah.
Then
but here I'm still retaining both x and k, but I'm still guaranteed positivity.
No, I'm only summing over levels, occupied levels. It's still a function of x and k.
Yeah.
Then the negativity goes away, and you can show that it's either 1 or 0.
Right. Yeah. But this coarse graining also
What?
Guarantees that. Like you can define a very precise coarse graining of the Wigner function, which makes it positive definite. Yeah, I think it's related, like the way you are suggesting. Okay, so anyway, so this is the prescription to compute the entropy. So I won't call it entanglement entropy. It's some entropy using the semi-classical GHT picture. Right. Okay. So now, of course, we have to ask, like, how do you solve these equations? So I mean, on the infinite line, it's easy to solve this equation. You just boost the initial phase space density. But if you have like scattering at this junction, and then there's a hard wall here, you have to take into account take that into account. And so basically, what one can imagine is that one can just think classically. And so we have particles which are propagating and getting reflected and transmitted with some probabilities. And so, so to find this density at any time, one just has to take account of like how many reflections these particles undergo, and before they're eventually transmitted. Okay. So so the solution on the infinite line is just this. So the solution at time t equal to 0 just gets boosted at every k. And okay, so the initial density is it can be written like this because it's non-zero only. So this is phase space. So the initial all particles are located between -n to 0, and in space in momentum space from -pi to pi, right? So this is the field thing, and then this density evolves in some way. Okay, so yeah, so without defects, it would just grow like this. And with defects, it's basically you have to just keep track of how many reflections and so on, and you can write it as a series. You can write a series solution. Okay, so we have a solution of the Wigner equation. So we know the phase space density at all times. Okay, so now I'll just show the numerical results where we. Yeah, so we have a similar formula for x less than 0. Like there also you just sum overall. Okay, so so now I will show results which compare between the microscopic simulations and what we get from hydrodynamics. So this is just the density profile. So initially the density profile was 1 inside the system and 0 in the reservoir, and then it changes in some way. And the points here are from the simulation, and the lines are from the hydrodynamics. Okay, and you can see very good agreement, except some oscillations and things are not reproduced. And this is the current at the junction. So for some time it just remains constant, and then it starts decreasing. So if you ask like at what time does it start decreasing? Okay, so basically from the system you have a flux of particles going out. Okay, so I mean obviously these are free particles, so the flux will be constant. But at some point, so there are some particles which are going to the left, and they hit the wall, and then they have to return, right? So that takes time 2n for the fastest particle to 2n divided by some Fermi velocity. So that's the. So after that, there are no more. The number of particles starts decreasing, and so the current starts decreasing. Okay. So this time, like 2n, it's basically the time taken for the system to realize that it's finite. And after that, you get differences from the infinite domain wall problem. Okay, so this is what I'll call the page time. I mean, so we'll now look at the entropy, the entanglement entropy. Okay, so now we compare the entanglement entropy from microscopics and with the hydrodynamic entropy. Okay. So the microscopic entanglement entropy, of course, we expect the system and bath will have the same entanglement entropy. From the hydrodynamics, this need not be equal. And let's just plot all of this. Okay. Sorry? I mean, there's no reason. This is not entanglement entropy. We know how to prove that they're equal, right? Hydrodynamics, it's not entanglement, so they need not be the same. Okay, so so now these are the. So let me just explain. This is entropy versus time. So the blue circles are from the exact microscopic. So initially it's unentangled and then it increases, and so this is what is the page curve. So this is from the hydrodynamics of entropy of the reservoir. Okay. So this, of course, initially there's nothing in the reservoir, so it starts with 0 entropy, and then it keeps increasing, and it keeps increasing forever. Okay. On the then, if you compute the system hydrodynamic entropy, that follows this blue curve, and you can see that this agrees with the microscopics extremely well. Okay, and this crossover is basically again happens at 2n, which is basically the time for the fastest particle to go to the wall and come back. Okay, so this is the page time. Okay, so the main point is that there is this remarkable agreement between the microscopic entanglement entropy and hydrodynamic system entropy at almost all times. Okay, yeah. Right, very short times maybe it's not good. At long times also, okay, you're saying there's some difference, right? Yeah, okay, so maybe I should show with increasing system size, it gets better, the agreement. Okay, so I mean, the bath entropy, I mean, it's like a Boltzmann entropy. I mean, this keeps increasing. And in some sense, this is like the radiation entropy in the black hole information. For
the conformal case,
but for all defects, it's more is exactly, it has the same feature. And this agreement is also there for all cases. Okay, the other thing is that we can compute, there are some power law decays at long times, which can be computed from hydrodynamics. Okay, so this is different system sizes, and here you can see that it gets better, right, for increasing system size. And the scaling is, of course, it's proportional linear in n, and if you scale with t by n, then they all collapse. Okay, so we can compute various from the hydrodynamics. The nice thing is that you can compute various asymptotics, like the short time is. I mean, so we have some series solution, but you can do some resummation and get the long time asymptotics and so on. So at short times, you get this linear growth, and we know these prefactors. And at long times, there's some power law decay, which is one for conformal defect and different from for other decay. Okay, so maybe since there's not much time, I'll just skip this. And I'll now, so right now I just talked about, okay, so this I just want to say that, okay, so we have talked about two definitions of entropy. One was the entanglement entropy, which is a sort of a microscopic, very quantum entropy defined for pure states. And the other entropy I'm talking about is actually a Boltzmann's entropy, which basically counts the number of microstates given given some specification of the macrostate. So in this case, given the phase space density, I can ask how many microstates are there. And that basically is the yang-yang entropy. Okay, so now I just want to talk about some other results. And these are for finite temperature states. Okay, so far I talked about the initial state, which was completely filled. But now we can ask, like, if it was not completely filled, if it was a higher temperature initial state, then what happens? Okay. So so one can consider two kind of situations. One is we still take a pure state, but at finite temperature, in the sense that let's say you can choose states from some grand canonical distribution. So you have the single particle energy levels, and you can occupy them according to a Fermi distribution, right? But you just take one such state and compute and see how the entanglement entropy evolves with time, and then do an average over a large number of initial pure states. Okay, so this would give you the entanglement entropy. The other thing you can do is start with a mixed density matrix and just compute the von Neumann entropy. Okay, so these are two different things. So in this case, for example, the entanglement entropy of system and bath would be exactly equal. In this case, they need not be equal. Right? The von Neumann entropy need not be equal. So now, so I'll just show you what we find.
Abhishek, can I ask a question? Can I ask a question?
Yeah,
So here in the first case, are you taking direct product states or are you taking some entangled initial state? When you take less than maximally filled.
Yeah, so basically I'm taking, see, I imagine I have this single particle energy states. I just occupy them with some probability and I get n number of states. I form a Slater determinant with that thing. Right, so you can just imagine like in my set of single particle states, some randomly chosen states are occupied. Is that clear? Okay, I'll continue. Any other questions?
Sorry, my question was if you take less than maximal filling, you can construct many initial states with the same density but different entanglement structure in the left half. In that case, what happen? Do the dynamics agree? The entanglement dynamics agree? Entropy dynamics?
Yeah, that's what I'll show.
Okay.
Yeah. Right. Yeah. So yeah.
Path.
Yeah. This is system. Oh, sorry. This should be. Yeah. Sorry. This is a typo. So it should be system is not equal to bath, and both should be subscript should be Vn. Okay. So now let me just explain this plot, which is again the entropy versus time, and there are different lots of different entropies that are plotted here. Okay, so first of all, this curve is just the entanglement entropy as defined here. So this follows the page curve, the entanglement entropy, and of course this is independent of whether we do it for system or bath. It's the same. Then this curve which goes like that is the von Neumann entropy of the system, and then this one is the von Neumann entropy of the bath. Okay, so those are quite different. Okay, so the bath, of course, initially there's nothing, so it starts from 0 von Neumann entropy, while the system it starts with a finite von Neumann entropy. If it's high temperature, it will be almost log 2, and then it follows this curve, right? Eventually, there's nothing in the system, so it goes down, while the bath saturates to some value. Okay, so this is the same thing plotted on linear scale so that you can see the differences and everything more clearly. So this is von Neumann of the reservoir, and this is von Neumann of the system. And then what is also plotted is this what I call the yang-yang entropy, which is this green curve, okay, from hydrodynamics. And there's a dashed line here, which is for the system also from hydrodynamics. Okay, so you can see that the microscopics and the hydrodynamics agree extremely well. Okay, so so now here I've said modified yang-yang entropy because originally I wrote some formula, and here we'll use some slightly different formula just for the bath part. Okay, for the system part, it's the same yang-yang entropy. For the bath part, we have a modified formula, and in the remaining 7 minutes, I'll try to explain this, how one can understand this modified formula. Okay, so this is true for, this works at all temperatures. So this is the main summary. Von Neumann entropy is reproduced by this modified hydro entropy. And this is another interesting thing, that early times, the entanglement entropy agrees with the bath entropy, while at, sorry, this should be late times, the entanglement entropy agrees with the system entropy. So let's now try to understand why this yang-yang formula reproduces the von Neumann entropy so well. Okay, so so to do this, basically we let's say we so let me first tell you what the modified entanglement entropy formula is. Sorry, modified yang-yang formula is. So this is the entire line, and let's say this is the system which has size n, and then this is the reservoir, right? So what we do is, okay, so this is system and this is bath. Okay, so now the bath, we divide it into cells of size, let's say 2n. Okay, so this is 2n, and then this is 2n, and so on. And then we take the this phase space density in each of this and just put it, fold it to this region between 0 to 2n. Okay. And for each of these parts, we have some weight factor, which is this this factor. Okay, so fk into 1 minus rk to the power s plus 1. So s just indicates which one we fold. So if we fold this one, we do it like s times. This one we do s minus 1, and so on. Okay. So okay, so this is how we create a modified phase space density by folding in all these phase space densities with some appropriate factor. RKs are the reflection coefficient. Okay, so there's a transmission TK, and RK is just 1 minus TK. Okay, so this is how we construct this modified, and then we compute using this. We compute the local entropy, which is by integrating over all k between 0 to pi, and then we integrate over x, but not over the entire bath, but just between on this cell. Right now, we have folded all these densities into this region, and then using that, so now the integration is only between from 0 to 2n and not from 0 to infinity. No, I mean, it's just for the computation. I mean, there are no physical partitions. It's just for the computation. I'm adding, like, I let n evolve as it was before. Then whatever n value was here, I just put it back here. But reflection is with still this single impurity here, the single defect. It's the same problem as before. These are just like artificial partitions, which I just do for the computation. Okay, so this is how we, and this is what works perfectly. Like, this reproduces the microscopic one-Neumann entropy completely. Okay, so now we want to understand why this happens. And for this, it's what we do is look at the evolution of the eigenvalues of the correlation matrix. Okay, so this is a so this is a movie which shows basically how the eigenvalues of the correlation matrix in the system and in the reservoir evolve with time. Okay, so okay, I should have started it from the beginning, but at t equal to 0, basically it's in the system. It's all it's a fully filled. So it's a diagonal matrix with 1. So all the eigenvalues are 1. Okay, so it starts like this. Okay. Yeah, so you can see that it starts with 1, and then a new eigenvalue emerges. There are some eigenvalues lying on this vertical line, but and then another eigenvalue. So all the eigenvalues are on this plateau. Then the new plateau emerges. Then another plateau emerges, and then there are some eigenvalues lying on these lines. Yeah, so the plateau values are exactly given by this reflection coefficient to the power s plus 1. Okay, so the first plateau is just rk, the second plateau is rk squared, the third is rk cube, and so on. Okay, and these fronts, you can see they are moving at some speed which actually decreases with time. And this, okay, so now, no, they're changing speed. Okay. And from hydrodynamics, we can understand these plateau values, and also as also how the speeds change. So this we can understand completely. Okay, and then using this understanding, we can understand why the entropy is given by this Yang formula. Okay. So now let me try to explain this. So the semi-classical derivation of eigenvalues. So how can we understand these eigenvalues from a semi-classical picture? Okay. So basically, okay, so let's say we first choose initial n single particle levels in such a way that F alpha is the mean occupancy. Then the correlation matrix, it's easy to show that it's, I mean, each of these states, supposing it evolves in time with the full Hamiltonian, then the correlation matrix is basically given by this object. Okay, so, and it has X and Y are in the systems which has n sides. So it's an n cross n matrix which has n eigenvalues, which are the eigenvalues of the collision matrix. Okay. So now equivalently, I can one can write this instead of looking at this matrix, one can actually look at something called the overlap matrix, which I learned from Shotto. So if you look at this matrix, which instead of summing over the states, if you sum over the sites, then you can, okay, I'll just take 2 minutes. Yeah, so this matrix equivalently also has information on the eigenvalues. So now you can compute this in the system or in the bath. So in the system, you sum over all sides in the system or also on all sides on this bath, and then this gives the eigenvalues. So now for pure state, you can show that these eigenvalues are trivially related in the system and bath, and that's why they have the same entanglement entropy. Okay, so this is pure state. This is true. This is not true for the mixed state. Okay, now, I mean, okay, so now supposing you choose your initial basis states as formed by this wave packets. Okay, so you can construct like instead of plane waves, or you can construct a basis which is localized both in space and momentum with some spread h bar. Okay. So in this, and then these wave packets will basically behave like classical particles and do not spread significantly. And when they arrive at a defect, this kind of split, and there are like 2 parts. Okay, so after, I mean, for example, this is an example of a wave packet which initially started in this system, and after like 10n, n is the system size, 10n times, it has split into, because it has undergone 5 reflections. So now there are 5 peaks here. Okay, and then from the, so you know what the wave function is, and then you can compute what are the heights of these peaks, and they're exactly given by this. Okay, and if you sum them, they're exactly this factor 1 minus RK to the power 5, which basically appears in the modified entropy formula. Okay. So basically, this is the proof. I mean, then basically you can write what the eigenvalues are. I mean, these are precisely the eigenvalues, the phase space in this wave packet basis. And there are exactly n of them, because your states are localized in this initial states. There were exactly n wave packet basis states. So these are actually the eigenvalues. And from this, you can, by summing over all the eigenvalues, you compute the Yang-Yang entropy. Okay. So this gives a kind of semi-classical derivation of the Yang-Yang entropy. In the system, there's always 1 peak, so it's the same. But in the bath, you get a modified formula. Okay, so these are my conclusions. I'll just leave it here.
For non-interacting fermions, you usually have a relation between entropy and this number variance.
Yeah, I think I didn't show that slide. Yeah. So I mean,
so we also go here. I mean, this still holds here, I suppose. I mean,
okay. So I mean, in principle, there's this a series in terms of the cumulants. Sure. But yeah, like for large n, this is already just the second moment is quite. I mean, this also we had. I didn't show because.
So that means that you also see the same kind of behavior.
Yeah, the number fluctuations also shows the page curve. Yeah, it's a simpler object to look at.
Yeah, that's.
Yeah.
Other questions? Yeah, please. Hello.
Yeah, so my question was this S hydro that you're computing, is it correct to think of it as Shannon entropy on this discretized phase space?
Yeah, I mean the Yang-Yang entropy, you can think of it as a Shannon entropy. Like you can if you maximize the von Neumann entropy subject to the constraint that the phase space density is specified, then you get exactly the the yang-yang entropy.
But then I will get some non-zero answer even if I was having some classical particles and I just discretize the phase space and compute this.
No, so what is your question? I mean, like whether, yeah, you can construct some entropy which will be non-zero even for a classical system. Yeah, that's true. I mean,
Yeah, all I was trying to understand is why it matches so well with the von Neumann entropy, like the physical.
okay, so that's what I tried to explain, like using this semi-classical picture.
So Abhishek, I have a question. I mean, so in the original page curve of black hole,
Yeah.
so there, I mean, so here the time scale is very clear. This is 2 times n, which
Yeah.
is the reflection time basically from the left side. So in the black hole context, what is the time scale there? Is it the somehow to reach the size of the black hole? Or
Gautam should say. I don't know, I think.
For the Schwarzschild kind of black hole, it goes like mass cube.
Mass cube,
Yeah.
Right.
Yeah, I don't know if there's a similar explanation. If there's no, I don't think it's, yeah, it's completely
Yeah.
different.
Okay, so if there are no other questions, so let's thank Abhishek again.